In this video, we'll be looking at differentiating simple expressions and evaluate dy dx by working through examples of varying difficulty. We start off by reminding ourselves that when we are finding dy dx, there's a simple rule we need to follow. We get the power down and we deduct 1 from the power. The notation we use is dy dx. So we multiply by the power and then deduct 1 from the power. So to start off with, we've got y is 3x to the power of 4. So dy dx will be 4 times 3 times x to the 4 minus 1. There it goes. I'm deducting 1 from the power. So this is giving me 12x to the power of 3. Moving on to the second example, dy dx will be 18x squared minus 20x. Y is 5x. We will write this as 5x to the 1. So dy dx will be 5 times 1 x to the power of 0. We know that x to the power of 0 is 1, so this is simply 5. This is an interesting example actually because it confirms that this is a straight line with a gradient of 5, and we know that the dy dx expression represents the gradient. So we confirm that the gradient is always 5. It's a straight line. In the next example, we've got y is root x plus 3. I will first write it in index form as x to the half plus 3x to the 0. So we multiply by the power and then deduct 1 from the power to get a half x to the minus a half. And for 3x to the power of 0, if I get the 0 down, 3 times 0 times x to the minus 1 will simplify to a half x to the minus a half plus 0. So the derivative of 3 and actually any constant will simply be 0. In y is x plus 2 times x minus 4, I will have to start by expanding. So I say that y is x squared minus 4x plus 2x minus 8. I will collect like terms to get x squared minus 2x minus 8. And so dy dx will be 2x minus 2. The derivative of negative 8 is simply 0, as we said before. And then in the last example on this slide, we've got y is 3 over x minus 1 over 2x cubed. The first thing to do is write things in index form. So it's 3x to the minus 1 minus a half x to the minus 3. So we get the power down. So 3 times negative 1 is negative 3. Deduct 1 from the power, x to the minus 2. And then the minus 3 comes down, so it's going to be plus 3 over 2 times x to the minus 4. If I deduct 1 from negative 3, this will take me to negative 4. Sometimes we are asked to find dy dx, but also evaluate it at a given point. And that's exactly what we're doing here. So once more, I will start by finding the expression for dy dx. So in this case, it's going to be 2x minus 4. And then I want to evaluate this at x is 4. So I draw the vertical line at x is 4. So it's 2 times 4 minus 4, which gives me an answer of 4. This is the gradient of the tangent to the curve at the particular point 4, 0. In the second example, y is x plus 3x plus 5. I will start by expanding to get x squared plus 5x plus 3x plus 15. I will collect the like terms to get x squared plus 8x plus 15. And therefore, I'm now ready to differentiate. I will get 2x plus 8. So I will now substitute x with the value of 1 to find the gradient at x is 1. It's 2 times 1 plus 8, which is equal to 10. Y is 2 over x plus 3 over x squared. As always, in these cases, I will start by writing my expression in index form. So it's going to be 2x to the minus 1 plus 3x to the negative 2. I get the power down, deduct 1 from the power to get dy dx to be minus 2x to the minus 2 minus 6x to the minus 3. and then I substitute x with 1. So when x is 1, we have negative 2 times 1 to the negative 2 minus 6 times 1 to the negative 3, and this gives an answer of negative 8. In the final example, we've got y is x plus 2 all squared over x. So I will actually start by expanding the numerator to get x squared plus 4x plus 4, all of it over x. I can write this on a term by term case, so it's gonna be x squared over x plus 4x over x plus 4 over x. This simplifies into x plus 4 plus 4x to the negative 1. I will now differentiate. The derivative of x is simply 1. The derivative of 4 is 0. The derivative of 4x to the negative 1 will be negative 4x to the negative 2. And we need to evaluate this at x is 2. So substituting x is 2 will give me 1 minus 4 times 2 to the negative 2, which actually turns out to be 0. We will actually see in another video that getting the y dx to be 0 is a particularly interesting point on any curve. That's something to be discussed in another video. Thanks for watching. If you find this video useful, please like it and subscribe to our channel. You can also leave a comment below to tell us what you think about it.